Our standard model of cosmology, the LCDM model for lambda cold dark matter that we've been discussing, seems to explain much about the universe. There are a few things, we've noted some of them, and I'd like to add, that it does not explain that we think a theory of cosmology should. I'm going to list 5 problems in this clip, and then we'll talk later about what, if anything, science has to say about how they are resolved. The first problem is the horizon problem. We talked about it. The problem is that the universe is isotropic. Well, isn't that good? Yes, that is good. We assumed it. It's the implementation of the cosmological principle. But how did it get that uniform? Remember, when we talked about the radiation era, we noted that at the time of last scattering, the horizon distance, 3 CT, was much, much smaller than the radius at that time of the surface of last scattering from which we are now receiving cosmic microwaves. What this means is that regions on opposite sides of the sky from us, at the time that the photons of the cosmic microwave background we are now seeing were emitted, had not been in causal contact. In fact, they're not yet in causal contact. They had not seen each other. They had not had any way to communicate with each other since the Big Bang. Now, in any system with any thermal or quantum fluctuations or whatever, there will be variations in the mean average energy. And through energy exchange, these will equilibrate. But they can only equilibrate if energy can be exchanged. The regions on opposite sides of the sky, in fact, the total, remember that 1 over root 3 of the horizon distance spans a degree in the sky. So regions more than about 3 degrees apart in the sky certainly had not been in causal contact when the light was emitted. So there was no way for them to have exchanged energy and equilibrated the temperature. So the very uniformity to one part in a few parts in 100,000 of the cosmic microwave background is a problem requiring a solution. There is no way to produce a system that will be homogeneous to within one part in 100,000 without allowing energy exchange. This is the puzzle called the horizon problem, number 1. Second problem goes by the name the flatness problem. What's the flatness problem? Well, you recall that we discovered that the universe is flat to a very good approximation. We did this using the cosmic microwave background, building a triangle whose long side was the 40-some billion light years to the surface of last scattering, and notice that the small angle approximation works. Good. So this tells us that omega 0 is either 1 or very close to 1. If it's exactly 1, the universe is exactly flat. If not, then R0, the measure of the curvature of the universe, is very small. Why is this a problem? Well, it's a problem because we have this interesting property of the Friedmann equations. So here I write the definition of omega, right? Omega is the ratio of rho divided by the critical density. This with an h squared is the critical density. This is the definition of omega. I'm going to, for simplicity, imagine that we're living in a completely dust universe, so that rho is the rho of dust. And in a dust universe, we saw that the energy equation, essentially Friedmann's first equation, can be written in this form. Omega here is the density parameter of the dust, and this is the contribution of curvature. Now, combining these two equations and doing some algebra that's too messy for me to reproduce here, we find that omega and at any given time and the scale factor at any time satisfy this interesting equation over here. So omega and A are related to omega 0 by this equation. Basically, you write this equation at time t with A of t and omega of t. You write the same equation with A of 0, which is 1, and omega 0, and play with them, and you find this equation. What does this tell us? Well, first let's check that it's consistent. Set A to 1. The denominator here is omega 0 minus omega 0, 0 plus 1. You find A is 1. Omega minus 1 is omega 0. Okay, this equation holds at A equals 1, which is t equals 0. As you go into the past, A is very, very small. Now, if omega 0 is exactly 1, then this is 0. Omega is 1. Exactly, that means k is exactly 0, and in an exactly flat universe remains flat. But what if omega 0 is off? Remember, we have some errors in our measurement of omega 0. What if omega 0 is 1 to within, say, 1%? Well, then, as you look deep into the past and say A is a billionth, then omega minus 1 is a percent. A billionth is much less of a percent is much less than omega 0, which is almost 1. So the second term in the denominator is negligible. For small a, we can throw it out. And then at very small a, the approximation is that omega minus 1, well, omega is 0 is about 1. Omega minus 1 is approximately a times omega 0 minus 1, which means that if omega 0 is off by a percent from being 1, omega must be off from being 1 by about a billionth of a percent. And as a gets smaller, the precision with which omega needs to be close to 1 increases proportional to a. What this means is that if we observe omega 0 to be 1 to within a few percent, it must have been exquisitely finely tuned to be almost precisely 1 in the early universe. So this sounds like an aesthetic problem, because it's just a question of someone set the initial conditions, whoever threw the rubber ball must have tuned it so omega was almost exactly 1, or maybe exactly 1. But we don't have a physical reason for that to be, for omega to be 1. If we had one, that would be very pleasing to us. So this is our second problem, the flatness problem. Why is the universe so flat? Third problem. Third problem is called the Relic Problem. We talked about the transition at 10 to the 15 GeV, where there's a symmetry-breaking transition from a grand unified theory to the standard model of particle physics. And as part of the dynamics of that transition, we expect the formation of so-called topological defects. And these would be characterized by the fact that they carry magnetic charge. Magnetic charge is something you might not have heard of. These are particles, very massive particles, which have the property that they behave like the North Pole or the South Pole of a magnet, but just the North Pole without an attendant South Pole. This is called magnetic monopoles, and we have not observed any such things, which is why you have not heard of them. They would be extremely massive, but also completely stable. They could not decay because this magnetic charge is conserved. It's a strange kind of topological conservation law, but it's conserved. So a magnetic monopole, once formed, would be stable, and we can compute the expected density of such objects because we know how to predict the density of particles that would have been formed in this transition. These particles, if they exist, would be rather easy to detect. We have tried and we have detected none. So where are all the monopoles? Problem number 3. The fourth problem is another one we've already mentioned. This is the question of how it is that when the electrons and positrons all annihilated, there were electrons left over. If there were equal numbers of electrons and positrons, then after annihilation there would be no electrons, and clearly there are enough electrons to produce all of the hydrogen atoms in the universe. Equivalently, one can ask the same question about protons and antiprotons, or quarks and antiquarks. And somehow, at some early point, there must have been an excess of quarks over antiquarks, of electrons over positrons, so that after annihilation, everything in the universe is made of the leftover, this discrepancy. So this problem is the problem of baryogenesis, the production of baryons, or leptogenesis, the production of leptons. It turns out that through the weak interaction, if you have an excess of electrons over positrons, this will lead to an excess of protons over antiprotons, so either of the two will do. In fact, modern theories suggest that leptogenesis occurred and then that leaked over into the baryon sector. But there's a problem. There are two. One is that the laws of physics are almost symmetric to within pretty high accuracy. It was only in the 60s and 70s that we discovered the small violations in the weak interaction of the symmetry under exchange of a particle with an antiparticle. So an electron has exactly, that's not violated, the mass of a positron, and most reactions that involve an electron, if you flip all the particles to their antiparticles, will produce a positron with exactly equal probability, but there's a small violation, a very small violation. Now, this violation is not in itself enough to generate unequal numbers of electrons and positrons, because, as we saw, in thermal equilibrium, particle states are just energy states, and if there is any reaction, the rates might be different, but if you give a system enough time, energy will be partitioned equally across all degrees of freedom, and there will be exactly equal numbers of electrons as positrons at any energy. And so, as enunciated by Andrei Sakharov in the late 60s, there are three conditions that a theory must meet in order for there to be an asymmetry between the number of, say, electrons and positrons, or protons and antiprotons. And those three conditions are: you must have a violation of charge conjugation symmetry, the symmetry between particles and antiparticles. There has to be some interaction that is not invariant. Otherwise, of course, any prediction you make has to be symmetric. Furthermore, you have to have a violation of time reversal symmetry. You need a violation of time reversal symmetry because, of course, you're moving from a symmetric state. At some point, you had a thermal state with equal numbers, and somehow you generate unequal numbers. And then the third condition is you have to be out of thermal equilibrium. The universe has to violate thermal equilibrium. We saw that everything equilibrates if you give it enough time, but in the context of an expanding universe, there might not be enough time. And so we need a model of physics that satisfies these three conditions. Now, we have, under certain circumstances, for example, the electroweak transition was thought, the weak interactions are almost certainly involved. That is where the universe violates these symmetries. But it was thought that the electroweak transition, in which the Higgs field acquires its expectation value and the W and Z bosons acquire their mass and so on, that if this reaction were to proceed via supercooling and bubble nucleation, then possibly at those bubble walls one would find in non-equilibrium physics enough to generate the observed discrepancy between baryons and antibaryons. It seems that there are difficulties, and we do not at the moment have a satisfactory theory of baryogenesis or of leptogenesis, and so this problem is one that I leave for you to solve. I should point out that we know that the universe is made out of protons and electrons, and all of the hydrogen atoms in the universe, or a huge majority of them, are protons and electrons rather than antiprotons and positrons. It would be difficult a priori to distinguish, although if an antiproton meets a proton, then they of course would annihilate. But could you have a galaxy made completely of antimatter somewhere out there in the universe? In principle, it would be hard to exclude that, except that there is a large flux of cosmic rays, of high-energy charged particles that reach us, that originate from distant galaxies. And these are, to a huge preponderance, protons rather than antiprotons. The small fraction of antiprotons is well explained as being the result of collisions en route to us. And so we have pretty good evidence that all of the galaxies and all of the clusters we see are made of hydrogen and none of antihydrogen. And yet we don't know how this came about. So we do not have a satisfactory model of baryogenesis. Something for you all to figure out. And the fifth problem is the problem of the cosmological constant. In the cosmological constant, remember I said, can be thought of as an energy density of the vacuum. And I gave you an example as to why an energy density of the vacuum would be equivalent to a negative pressure. I suggested that if you took two plates and separated our vacuum in between them from some other vacuum with no vacuum density, energy density, then the system in lowering its energy would try to squeeze those plates together, generating a negative pressure. Now, I didn't invent that great idea. In fact, there is such an effect that is measured in the following way. You take two conducting plates, dangle them in a vacuum. Essentially, one way to and then you find an attractive force between them. Now, one way to understand this is that the quantum fluctuations of the electromagnetic field between the conductors lead to a positive energy density, contribute to a positive energy density. Calculation is slightly outside our range. And not completely a issue of consensus. What is true is that there is an attractive force that's been measured. And the idea is that in the conductors, the electromagnetic fields are zero because they are conductors. And in between them, there are quantum fluctuations. This leads to a positive energy density, and therefore the negative pressure that attracts the two plates. You can use this idea that quantum fluctuations are responsible for the energy of the vacuum to make a calculation in the quantum field theories in addition to electromagnetism that describe our universe. And dimensional analysis in these quantum field theories suggests a natural value for the cosmological constant, up as usual to multipliers of order 1, and up to coefficients of order 1, you expect naturally that the vacuum energy density will be on the order of, well, the only natural scale, the Planck scale, the energy density, the thing with units of energy density that you make out of Newton's constant, the speed of light, and Planck's constant. This is the expression in terms of m Planck, this is the value, and this is off by about 120 orders of magnitude from the observed value. So, again, you can say that this is just the conditions of our universe, but if we are going to have any natural or theoretical explanation for what lambda is, when I was a graduate student, we all thought lambda was 0, the cosmological term was 0, and theorists were trying to think of theoretical reasons, symmetry considerations that would cause it to be 0. Supersymmetry was a leading candidate of those. Generating a universe in which the parameter is non-zero, in which case these are the natural dimensional analysis, what you need to explain is why the coefficient is such a tiny number. And this dimensionless ratio between the expected value of lambda and the measured value of lambda of 10 to the minus 120 is very hard to generate. We have no real understanding of why the cosmological constant is so small. We will talk maybe in the last clip of some contexts in which people are thinking about it, but these are the 5 problems, I think, with lambda CDM cosmology. The story is not completely done. Let's see what else we can say.